The following three questions are conceptual questions based on potential energy versus distance curves. The first one asks, in what region is the force on the particle positive? Force is related to potential energy by a negative derivative. And graphically, this can be represented as the negative slope. So to answer question 10, we're going to look for a region on our U-curve where the slope is going to be negative so that when we take the negative of a negative, we'll get a positive. Looking at the curve, the slope in region A is 0. The slope in region B is a positive value. The negative of a positive value is a negative, so the force will be negative in region B. And since it's going back to region A, the slope here is 0, so there's 0 force on the particle in region A. For region C, this slope is negative, and so if I were to calculate the negative of that, the negative of a negative is a positive, and that's actually going to be our answer. So C. But just continuing on, in region D, we again have a positive slope. The negative of a negative of a positive gives us a negative, so force is also going to be negative in region D. And the particle never actually reaches region E because it doesn't have the energy to get up here because its total energy is represented by this dashed line, but if it were to do so, there would also be 0 force on it. For the next question, we're asked, in which region is the speed constant? Well, to keep the speed constant, there must be no force acting on the object, otherwise it'd accelerate. And so we already found that region A has 0 force. One confusion might be, how did we know the answer was A versus E? And the reason is actually because of the answer for problem 12. Problem 12 asks, at which point does the object stop and turn around? That occurs when the total mechanical energy line intersects our potential energy curve. So the object turns around here, therefore never actually reaching it to zone E, which is why the answer for 11 is A. So now putting in all of our final answers, the turnaround point is the intersection, and that occurs in region D. The next question has a pendulum swinging back and forth. We're told information about the mass and the angle and the length of the pendulum, and we're asked what is the work done by the tension force. And this is actually a little bit of a trick question, because if I were to draw the free body diagram for my object, I have a force of gravity pointing exactly downwards and a tension force pointing in the direction of the string. However, work is force dot displacement, and the displacement of my object is always tangent to the circle. And so if I take a closer look, the tension force and the direction of motion are always going to be perpendicular to each other. And so if I were to write out this dot product as my tension force times my displacement times cosine of the angle between them, the angle between them is always going to be a 90-degree angle, and cosine of 90 is 0. So the work done by the tension force, no matter where we look on the circle or the pendulum, the circle the pendulum is swinging out, the work done by the tension force will be 0. This next problem can be thought of two problems in one. We have an object some height h above the ground. It compresses a spring and then is released from rest. It moves down the hill that has no friction, and then once it gets to this point right here, it encounters a region with friction, slows down, and comes to a stop. We're asked what is this distance the object must travel before coming to a stop And to solve this, we can solve the first problem as a conservation of energy problem, where ultimately what we want to try finding is what is the speed of our object right before it enters the rough patch. Setting this up as energy initial is equal to energy final, the initial is at the top of the hill before the object starts moving. It's not moving, so it has no kinetic energy. It is above the ground, so we have a gravitational potential energy. And there's a compressed spring, so there's an elastic potential energy. At the bottom of the hill, the object is moving, so there will be a kinetic energy. It's at the ground level, so there's no gravitational potential energy, there's no more spring, and there's no friction yet, so the only energy there will be this kinetic. We can solve now for the velocity. Plug in the numbers. I'll drop the units just to keep things, there's not a lot of room. And if I were to put this into a calculator, I get 12.15 meters per second. So part 1 of the problem is now done. We have a velocity right before the object enters the rough patch. Once it's over here, it's come to a stop, and we can find from this information the acceleration that causes it to stop by applying Newton's second law, where the only force acting on the object in the horizontal direction as it comes to rest is the force due to friction. I added in that minus sign. Let's just take it away for now. We'll add it back later. Solving for the acceleration, I have it equal to the coefficient of kinetic friction times g. So at this point, I'm set up with a kinematics problem. I know the acceleration, I know the initial and final velocities, and I want to find the distance. Using this kinematic equation, I can now solve for the distance. My final velocity is 0. I know my initial velocity. My acceleration is in the negative direction because it's slowing my object down. The object's moving to the right, so the acceleration must be in the negative left direction. L is my final distance, and I can say I start at 0. Rearranging this to solve for L, I have my initial velocity divided by 2 mu k times g. So plugging in numbers, putting it into a calculator, I get that L is equal to 10.76 meters, which when I round is equal to 11.